I'm going to talk about Hylé and how we're rethinking base layers for 2025 and the following years. So my name is Lancelot. I'm the co-founder and CTO of Hylé. Previously, we were working in the Starknet ecosystem, doing something with like Lego, digital Legos. What I'm going to be talking about today is like what we see at Hylé for trends in crypto and how these trends help us rethink the future of blockchain, how to do storage, how to do identity, how to execute stuff on chain, and then kind of give you what we think is like the state of the art implementation of what a blockchain for ZK is, kind of. And along the way, touch on a bunch of topics. So the idea that what we realized at Hylé that a change is coming, and there's two components to this. The first one is that ZK is the end game. Zero knowledge proof technology is rapidly reaching like real-time capabilities. It's not there yet, obviously, but the tooling is improving a lot. And like where a few years ago you had to write your own circum circuits from scratch if you wanted to do anything with ZK. Nowadays, you got ZK VMs that are working pretty well. You can write regular Rust code, and pretty soon, hopefully, we'll have like almost real-time or real-time proving. And in the future, maybe like instant proving on smartphones, things like that. The second change that's coming is that we're moving towards a signature by default world. Digital signatures are growing increasingly common. Like it's a general trend, but one of the reasons why this is happening is like AI slop. If you want to make sure that some content comes from a human, you got to sign it, and there's even like hardware signatures embedded in the phones, or in like cameras when you take pictures and things like that. And ZK is just signatures, but programmable. So it opens up a lot of doors. And again, like a few years back, only emails were really signed or passports. Nowadays, you got invoices coming, contracts, banking. Pretty soon you have photos, voice, health data, IoT, kind of everything. So what happens if you have both of these things happening at the same time and moving in an exponential direction? Well, ZK and signatures, what they allow you to do is to bring new classes of real-world assets on-chain, because anything that's signed plus ZK can be used to trustlessly bring it on-chain and then be operated on. But, because there's but, well, the question is how do you build a network to enable this kind of like cool future? The problem is that you can't really do this on existing blockchains for reasons we all know. Blockchains have poor performance, the UX is not great, you have a bunch of different wallets, and because of fragmentation, especially in the Ethereum ecosystem, this all becomes much worse because then you have trade-offs that you need to understand to be able to make security problems, things like that. The solution to all of these problems is to do kind of like an iPhone thing where basically we have separately the technology to do all this, but we need to bring it all together. So the three things you really want to do is first, the problem is that applications are limited both in terms of like the size of the code and the complexity of the code you can write, and in the storage size. The solution to that is to just have no actual storage of that on chain. The second part of the problem is that using the chain requires you to use like a mnemonic, 24 words, things like that. Using a wallet, it's very annoying and very hard for like onboarding new users. And the solution to that is identity abstraction. And the third big problem is slow throughput, and that's mostly being bottlenecked by execution layers. The solution there is to just remove execution. And that's kind of what we're doing in Hylé. So let's get going into that. First thing is no storage. What does actually that mean? Well, it means that we're doing commitments, just like the ZK rollups on Ethereum. On Hylé, all that we store is the state commitment, the tip of the iceberg, and the application state can live kind of anywhere. We don't really care. And that's where you're going to store like most of the actual data, 99.9% of it. So that's pretty straightforward. The second thing is how do you do identity abstraction? How do you remove the wallet? How do you remove MetaMask from the equation? So the question is, what is a wallet? A wallet, conceptually, it's basically like a nonce, so a number used once, and the secret is something that you know. And secret is just something that you have or something that you are, and the nonce is kind of a bottleneck. And there's a bunch of ways you can do more interesting things here if you have if you no longer have limitations on like code size and code efficiency. The big one is things like multi-dimensional nonces or like using UIDs as part of your transaction nonce, so that you don't have to query the state of the chain before you can send a new transaction. You just make a UID, you can be sure it's unique, and you can just send your transaction and things just work. And in terms of like secrets, well, there's a whole bunch of other secrets by the private key. You could have passwords. You could have one-time password over email, like you have on like Medium. You could do passkeys with like WebAuthn and things like that. You could have biometrics authentication. All of those things can be used once you have ZK, because ZK allows you to actually verify them without revealing the secret potentially, which could then be reused by anybody, the same way a private key, public key pair works. And on Hylé, like this can already be done to a certain extent with account abstraction, which still isn't live on L1, Ethereum L1 anyways, but happens on some L2s. The idea for account abstraction is that your secret is wrapped in ZK proof that's sent to a smart wallet, but your actual on-chain identity is the address of the smart contract. With identity abstraction, what happens is that the smart contract actually manages several identities. And so potentially you could have a single smart contract know you by different names depending on the secret you use interchangeably, or things like that. You have the ability to have much more complex authentication credentials than just a single address of a smart wallet. They're like a completely different type of entity. The final thing, and the most difficult thing, of course, is to know how you remove execution. And the trick here is to do pretty much just pure sequencing. And so I'm going to talk to you about based rollups. So the key insight is that once you have sequencing, the state of your chain is deterministic. So to give a bit of an example here, you don't need to actually execute what I'm going to say to be able to understand it. If you imagine a transfer of tokens, you start with John that has 5 tokens, and then you do 3 transfers in a deterministic order. Anyone reading the chain can reconstruct that the end state is this particular end state. How you do the execution doesn't actually matter. All that matters is that the transactions are sequenced in the correct order. And so sequencing is actually kind of all you need for for blockchains to operate in a way. And that's kind of what Celestia has been doing, for example. If you look at what they're actually shipping, that's kind of like just sequencing as a service. And so then you get into this whole framework of, well, what does this mean for rollups? And so I'm going to give you like a quick primer on 3 concepts plus the new thing we're introducing. The first is like ZK and optimistic rollups, how they work. Sovereign rollups, which is a Celestia concept. Base rollups, which is on Ethereum L1. And the secret new thing that we're going to be enabling. So legend of this diagram, if it's a clown, then it's because it's not secured by the L1. If it's a clown with glasses, it's kind of secured by the L1, and otherwise it's the L1. So ZK and optimistic rollups, they usually have their own sequencers. They're completely independent from the L1. The execution usually happens also on the layer 2, but it's verified by the layer 1, either with like fraud proofs or with ZK proofs. The DA can kind of vary. Some rollups are sending the data to Ethereum, some are not. And settlement happens on Ethereum. That's where like the truth of the state commitment lies. Sovereign rollups, they're doing things a little differently. The sequencing and the DA are provided by the L1 chain, which is Celestia in that case. But the execution happens completely off-chain. There's like literally no verification. I need to change this graph because this should be a clown as well. And there's no, in the case of sovereign rollups on Celestia, there's no settlement by default. If you want to settle something, you have to become a ZK rollup on top of Ethereum as well. Base rollups are kind of a new thing that are not quite out yet, but people are working on in the Ethereum ecosystem, where the sequencing happens on L1, so people send transactions to Ethereum directly. The execution happens on, somewhere else, usually on like an application centralized server, but then is verified by fraud proofs or ZK proofs by Ethereum. Ethereum is your DLL because that's where you've sent the transactions, so that's where you can find whatever happens. And the settlement is also happening on Ethereum. So almost everything happens on Ethereum with base rollups. You have 2 main drawbacks. The first is that you have to maintain a smart contract yourself to be able to verify the execution. And the second is that you actually don't get any kind of native composability. You can't interact atomically with any other Ethereum contract. You can't reuse your MetaMask wallet very easily. You have to bridge. On Hylé, we're doing something slightly better than that because everything happens natively on the L1 directly, and that's a little more convenient. I'm going to get into how we do that. I'm going to skip those because that's going to take too long, but basically there's different ways to do data availability, and Ethereum consensus is pretty bad at it. The top of the line thing is something called, it's like the DAG-based solutions that were pretty cool 3 years ago, like Narwhal and other consensus algorithms. And nowadays on Hylé, we're using something called Autobahn, which is kind of like state of the art, something that Sui is also experimenting with. And the diagrams come from Commonware, which is also doing like stuff in this space. I'm not getting into that because it's going to take too long. So back to sequencing. The question is, how do you verify execution? You can execute everything on chain. That's like Ethereum itself, or like native rollups. If you have the execute opcode, you got frog proofs, which require re-execution. And usually people like re-implement the EVM inside the EVM, which is kind of wasteful. Or you have ZK proofs, which give you much more like scale and which give you privacy and things like that, which is very interesting. And so the solution we chose at Hylé was obviously ZK proofs because we think they're the best execution layer. And the way that ends up working out is that the user sends a transaction to the chain, which leads to a new state commitment. And then every transaction is basically just a state transition secured by ZK proof. The chain doesn't need to know about the full state of the application at each step. It doesn't even need to know really what's happening within the transactions. It just needs to know that it changes the commitment. And everything happens on the L1. So from the developer perspective, it's super easy. And the security is not even a question because you just reuse all of the layer 1 security. You're not introducing any new trust assumptions. So where's the catch? The problem with ZK proofs is that, well, there's 3 problems with ZK proofs. The first is the composition problem. Usually it's difficult to call other contracts using ZK. The second problem is the proving problem. Like obviously it takes time and it adds latency if you want to prove something because we don't have yet real-time proving. And the third problem is parallelization problem. Like ZK isn't commutative in some sense. So let me get into those. First, composition. Usually if you were trying to write an application and you were trying to like write Tetris and you wanted to use a proof that somebody had like a CryptoPunk in like ZK Tetris, you'd have to do what's called recursion. So basically you verify the proof that you own a CryptoPunk inside your Tetris application. And that's very inflexible. If you want to change one of the two, you have to like register a whole new application. You have to change everything. You're not given very much flexibility. And it's also very hard-coded. You can't suddenly support another kind of NFT or something like that. Composability is different. Composability is where you have both being proven separately, and you can kind of replace either part and it still ends up working. And we enable that on Hylé with like some smart atomic composition of transactions because we're doing sequencing. The second big problem is proving time. Basically, like to give an example here, it's pretty straightforward. If you have an auction and the auction is ending in 10 seconds, you can send a transaction to the chain, but you don't have the time to prove it. If you have to wait for the proof to send the whole thing to the chain, by the time you've generated the proof, the auction will have ended. And so you will be sad. So that's the first problem, proving time. The second problem is a little trickier. It's parallelization. What happens here is that you and some other guy see the same state on chain. So in this example, the green thingy, and you both send a transaction. You take longer than the other guy to actually compute your proof for whatever reason. And so by the time your transaction arrives on the chain, he's already sent his. And because ZK proofs are like state transition from state commitment to state commitment, you can't actually settle your proof because you were expecting the green state, but the unchained state is now the blue state, which is entirely different. And we can't know that your proof is correct, and we can now transition to the red state for, for what we know, this is like completely invalid. So again, like you literally cannot have any kind of parallel transaction happening if you're doing pure ZK like that, which is, for example, the problem that Mina had. The solution to both of these issues is something we call pipeline proving, where the idea is basically that each user first sends kind of like a commitment. You send a blob transaction to the chain, and we just sequence that. We don't know really what's happening at this stage, but it gets sequenced immediately, and so you know in which order the transactions are arriving. Like I was saying earlier, because you know the order of each transaction, you can compute the state. You can like replay the chain. At this point, you can generate proofs safely because you know that the first proof will take you from the green to the blue state, and the first transaction, sorry, and the second transaction will take you from the blue to the red state. So the proofs you generate can actually be correct for these states. You don't have a parallelization issue, and you also don't have a proving time issue because you've sequenced your transactions before the end of the auction. It doesn't matter too much if the proof take a bit of time to arrive because we know what the state will be. It's just kind of an accounting thing at this point to actually settle the state. And so both of you guys are happy because you've both been able to send your transaction in time and you had no actual issue. And so this like new category of improvement on what a base rollup used to be is what we're calling unchained application, because you can kind of build applications that are actually no longer limited by the blockchain you're trying to write them on, which has been the problem so far. And because we're running on like ZK rails, you can really do kind of anything you want. I'm giving random examples here. You could do like a DeFi pooling protocol with permissionless private strategies with a centralized backend. You could do permissionless peer-to-peer on-ramp via ZK email or something like that. You could even have a fully on-chain game where the state of the game is kept secure by the player base with like no restriction on the kind of complexity of the code you can write because of ZK proofs. So that's it for my talk on unchained applications.